So first, recall that the natural exponential function f of x equals e to the x is a one-to-one function that has a domain in the real numbers from minus infinity to infinity. Now, because it's a one-to-one function, then it has an inverse, which is the natural log f of x log of x, okay, ln of x. Now, you can see the relationship here between the exponential and the reflection, the symmetric reflection, that is his inverse and the log. Because they're intimately related and one is the inverse of the other, then we have a couple of relationships between them that are going to be very important. One of them is the property of the composition. So both e to the ln of x is x, and log in ln of e to the x is also x. Okay, so this is a property of inverse functions. Now, from saying that y is equals to log of x, immediately we're saying, yeah, x is equal exponential of y. Okay, there's a relationship by defining one number as the log of another. Okay, finally, we can express, given a base or a number, real number b bigger than 0, we can express the exponential b to the x in terms of the natural log and the exponential with the Euler number. So we can write b to the x as e to the log of b power to the x, or e to the x natural log of b. Okay. Now notice that this creates certain ways where we're going to relate exponentials in different bases for their derivatives using this function, and coming from this we can also find out what the derivative for the log is. So summarizing that, those notions is the following theorem, which is the derivative of ln of x. So the derivative of ln of x is going to be 1 over x if we're assuming that x is positive. Okay, but if x is not positive, we can talk about the derivative of the log of the absolute value of x, and that also is going to be 1 over x, considering that x is different from 0. Now, if u is a differentiable function, then we can extend this idea by doing chain rule. And so if we have the derivative of ln of the absolute value of u of x, then we're going to have that this is just 1 over u of x times u prime of x, or u prime over u of x. So notice that there's also a little bit of symmetry between their functions and the derivative. If I have the log of x here, we can see the graph, and this is for the natural log of x. We can see that the derivative is also having some sort of reflecting behavior here. And the same happens with the log of the absolute value, which we can see the absolute value just reflecting the negative into positive. And we can see that log of absolute value of x works for both negatives and positive, and then we have reflections in terms of how the derivative is going to transform. Did you notice that in the positive numbers we have positive slopes, and so that's going to say, oh, okay, so we have a function that is positive all the time, and so that's why we have 1 over x over here. On this side though, because of how it's coming, notice that any point that you take is going to have a slope of tangent line negative, and so that's going to tell me, yes, this is going to behave like a 1 over x in a negative domain. Now let's take a look at some of examples that we can do when we take this derivative of logs. So we're going to find out what is the derivative of log of 4x, x log of x, log of secant of x, and log of x squared divided x squared. Okay. All right. So Let me write this here in the board before we move forward. So log of 4x, x log of x, where we're going to take a look at product rules, and log of secant of x, and the log of x squared over x squared. So notice that we're taking a look at different things: chain rules, product rules, and quotient rules. Okay, so we're gonna test with most of the things that we can dislocks, and we have the property, the general property, that the log of the absolute value of x, the derivative of this, is u prime over u. Okay, so we're gonna be using this a lot. Now let's solve a. A is log of 4x. So clearly we can identify that with this. So if y is equals log of 4x, we have that u of x in this case is 4x, and so u prime is going to be just 4. So the derivative y prime is just essentially 4 over 4x, which is going to be just 1 over x. So it doesn't matter if we have something inside multiplied, a constant multiplying, we're gonna get to the same thing. And that makes sense because remember that if y is equals log of 4x, you can write this with properties of the logs as log of 4 plus log of x. So the derivative of this is going to be essentially 0 plus 1 over x. Now let's go to the second one, where we have a product rule. So interactions with product rule are they might be nice if we have powers. Notice that in this case we have 1 times log of x plus x times 1 over x. So the derivative of this product is, it gets simplified to log of x plus 1. So very simple. Now let's go to number 3. In number 3 we have a composition again. We have or C, we have log of absolute value of secant of x, right? And so remember that we're essentially doing a chain rule. So this is a composition between the log and the secant. So y prime is going to be 1 over x, compose the secant. So 1 over secant of x times secant prime of x. Okay? So notice this makes sense with the u prime over u formula. And this is going to be the derivative of secant is minus cosecant of x cotangent of x. Wait, this is secant, not cosecant. So secant by tangent. So secant of x by tangent of x. I was thinking in cosecant for a second. Over secant of x. So now notice that I'm going to be able to cancel secant of x, and that's just going to be tangent of x. Okay? Now notice that there is more than one way to arrive to this conclusion. If you play with the trigonometrics and the properties of the log, you can do this for a very different route. We can write log of secant of x as log of 1 over cosine of x, which is what secant is, right? Now, using properties of the quotient, this is log of 1 minus log of cosine of x. Since log of 1 is 0, we can just write this as log of cosine of x. So we transform something from being in secant to being in cosine now. And so y prime is going to be derivative of minus 1 over cosine of x times the derivative of cosine, which is minus sine. And that's going to give me a minus and a minus a plus. So that's going to give me sine over cosine which is going to lead to a tangent of x. Okay. All right. So now let's go for the final example with the logs, and we're going to use here y equals log of x squared over x squared. So we have an impending quotient rule here, since we have two functions in that. And you can approach this in two ways. You can transform this using properties of the power, so you get 2 log of x over x squared, and then do quotient rule here, or you can just do quotient rule here and do chain rule. Okay. This one is going to be simpler for now, so I'm going to go with this one. Derivative of 2 log of x is going to be 2 1 over x, right, times x squared minus 2 log of x times 2x over x squared to the square. And so now this is 2x minus 4x log of x, and we have an x to the 4 down here. We can simplify one of the x, and this is going to be 2 minus 4 log of x over x cubed. This again is one way to approach this. We can always do chain rule, and so by doing chain rule directly here, we have derivative of log of square is going to be 1 over x squared times 2x, and that is the derivative of log of x squared, times x squared minus log of x squared times 2x over x to the 4. And this is essentially the same thing. Notice that you get to cancel 1x with this, or you get to cancel this x squared with this x squared, and so you get 2x minus, and on this side you get to do 2x log of x squared over x to the 4, and you can pretty much cancel out the x, and that's going to be 2 minus 2 log of x squared over x cubed. Notice this is the same thing as this if you use the properties of the powers for logs. Okay, so that's all for this part 1. Part 2, we're going to check what happened when we introduce exponential functions in the mix.